Hello everyone, welcome back to ZypherSpaceCore. In our previous episode, we studied how linear feedback shift register generates sequence, how feedback tape works, how maximum length sequence are created, and how LFSR are used in stream ciphers. At first glance, LFSR look extremely powerful. They generate very long sequence, very fast output, and sequence that appears random. In fact, their output passes important statistical randomness tests. So naturally an important question comes. If LFSR look random, then why they are considered insecure in modern cryptography? This is exactly what we will study in this episode. So let's begin. Now let us first understand why LFSR sequence appears random. Even though an LFSR is completely deterministic, its output still behaves statistically like random noise. This happens because the maximum length LFSR sequence satisfies the most statistical property called the Golomb's randomness postulates. These are three main properties. First property is balance. In maximum length sequence, the number of ones and zeros are almost equal. For an n-bit maximal LFSR, there are exactly 2 raised to n minus 1 ones and 2 raised to n minus 1 minus 1 zeros. For example, 4-bit maximal sequence of length 15, there are 8 ones and 7 zeros. So the probability of getting 1 and 0 are approximately equal. The second property is run distribution. A run means consecutive repeated bits. For example, 111 is a run of length 3, 00 is a run of length 2. In LFSR sequence, half the run have length 1, 1/4 have length 2, 1/8 have length 3. This distribution closely resembles the natural random behavior. Third property is autocorrelation. Suppose we shift the sequence and compare it with itself. When the shift equals 0, the correlation becomes maximum. But for other shifts, correlations become extremely small. This means the shifted variation of the sequence have almost like unrelated random sequence. Because of this property, LFSR sequence look random for statistical test. And that's why LFSR become very popular in communication systems, satellite system, radar system, and early cipher stream ciphers. But remember carefully, randomness does not automatically mean cryptographic security. Now, let us understand why engineers heavily use LFSR in hardware system. The first advantage is hardware efficiency. LFSR requires only flip-flop and XOR gates. That means the hardware distance becomes extremely simple. Even large LFSR can be implemented using very little cutleries. Then second advantage is speed. An LFSR produces one output bit during every clock cycles. This means no complicated arithmetic operation, no lookup tables, no heavy computation. So the generation process becomes extremely fast. Third advantage is low power consumptions. XOR gate consumes very little electrical power. This is why LFSR becomes useful in RFID system, IoT device, embedded system, and battery powered hardware. And the fourth advantage is scalability. As we increases the register length, the sequence period increases exponentially. For an n-bit maximal LFSR, the maximum period becomes 2 raised to n minus 1. So, even small hardware can generate extremely long sequence. This combination of simplicity, speed, low power, and scalability made LFSR extremely attractive in earlier cryptographic hardware. Now we reach biggest weakness of LFSR, and the weakness of LFSR is linearity. Recurrent relationship of LFSR is linear. This means that every future bit is generated using XOR combination of previous bit. Mathematically, a new next bit depends linearly on earlier bits. This creates a serious cryptographic problem. If an attacker observes enough output bit, the attacker can mathematically reconstruct the polynomial internal state and the future output sequence. For an L-bit LFSR, observing approximately 2n output bits is enough. This means huge period alone does not guarantee security. Even though the LFSR pass statistical randomness test and appear random to human, they completely fail computational unpredictability. And once the unpredictability appears, security collapse. This is exactly the reason why single LFSR are considered cryptographically broken. Now let us study one of the most famous attack against LFSR. Berlekamp Massey algorithm. This algorithm constructs the shortest LFSR capable of generating an absurd output sequence. Let us understand the process step by step. The step 1, the attacker collects the output bits. The attacker does not need the sieve, tape, and the polynomial. The only absurd sequence is needed. Step 2, the algorithm builds a temporary LFSR model. A new bit arrives, the algorithm checks whether the current model correctly predicts the sequence. If the prediction fails, the feedback polynomial is updated. The model becomes more accurate. After enough bits are observed, the algorithm coverages to correct the minimal LFSR. Finally, the feedback polynomial becomes known, the register length becomes known, and the future bit becomes predictable. The dangerous part is the attacker is computationally efficient. Even a large single LFSR can reconstruct it quickly, and this is why standalone LFSR are insecure. Now let us summarize exactly why the single LFSR fail in cryptography. The reason is next bit predictability. In a secure stream cipher, the future bit combines remain unpredictable, but enough LFSR output bits are observed, the future bits become fully predictable. The second reason is state recovery. This is secure system should hide their internal state. But in LFSR, internal state is directly related to the recent output bit, so the attacker can reconstruct it mathematically. The third reason is failure of semantic security. Suppose the ciphertext is generated using XORing plaintext with keystream. If an attacker recovers the keystream, the ciphertext can immediately be reversed back to plaintext. So the confidentiality completely breaks here. Therefore, a single LFSR should never be used alone as a cryptographic stream cipher. So, how did the engineers try to improve LFSR security? The main idea was to break linearity. One method is combining multiple LFSR together. Instead of directly outputting one register, the output are combined using nonlinear Boolean function. This increases unpredictability. The another method is irregular clocking. Instead of clocking every register during every cycle, the certain registers are clocked conditionally. This destroys the simple linear structure and makes attacker harder. The examples includes stop and go generators, alternative step generator, and stringing generators. Another approach is filter generation. Here, one long LFSR is combined with a nonlinear filter function. All these methods attempt to make sequence reconstruct much more difficult. Now let us study a very important real-world cipher called the GSM A5 bar 1. A5 bar 1 used in GSM mobile communication systems from late 90s till 2010s. For example, billions of mobile phones are around the world are protected using the cipher. It uses three different LFSR, different register length, and majority rule clocking control. Three registers are one with 19 bits, second with 22 bits, and third with 23 bits. Each register has its own feedback bits and its own feedback polynomial and its own clock control bit. Now, let us understand how this system works. During every clock cycle, the clock bits from the three registers are checked, a majority vote is calculated, and only the register matching the majority are shifted. This is called irregular clocking. The purpose was to break the simple linear behavior and make the attacker harder. After shifting, the output of all registers are XORed together to generate the final key string. So, many years later, the A5 bar was believed to be secure, but eventually the researcher recovered its weakness. In 1994, the theoretical weakness were published. In 2003, the practical attack successfully recovered the section keys. In 2009, the large rainbow tables made attacks much faster. Later, IMSI catcher attacks exploited GSM weakness in real-world surveillance. Eventually, A5 bar 1 became considered completely broken. This because one of the most important lessons in cryptography that complex looking systems are not automatically secure. Now let us compare LFSR with modern cryptographic generators. Modern systems such as CHARTA-20 and AES-CTR were specially designed for cryptographic security. Unlike LFSR, they are not linear. They resist next bit prediction, and Berlekamp Massey attacks does not work here. The modern ciphers also provide strong mathematical security, resistant against modern attacks, and formal cryptographic analysis. LFSR are still faster, simpler, and low power. But cryptographic security is much more important than raw speed. This is why modern systems replace standalone LFSRs. Even though the LFSR are insecure for the encryption, they are still extremely powerful in engineering systems. They are widely used in hardware testing, FPGA validation, communication scrambling, GPS spreading system, satellite communication, and simulation system. In this application, speed, simplicity, and pseudo-randomness are important than cryptographic security. So, LFSRs are not so obsolete, they are simply used in correct domains. So, let us conclude this episode that LFSRs are mathematically elegant, hardware efficient, and statistically random. Their sequence satisfy most important randomness properties, but randomness does not guarantee security. Because LFSR are linear, their output eventually become predictable. And once the predictability appear, the security collapse. This is why modern cryptography use nonlinear constructions like CHARTA-20, AES-CTR, and modern secure CSPRNGs. Thank you for watching CypherSpaceCore. If you enjoyed this episode, subscribe and support the channel.